We are the Way Humidification Performance Group. My name is Jennifer Haycock, and I worked alongside Spencer Gordon, Michael Green, Andrew Davidson, and Alec Chase to design and complete this experiment over the course of the semester. Our test objective is centered around trying to control humidity in an isolated test environment. The key question we aim to answer is, to what degree can we maintain humidity using two-way humidification? For those who may not know, two-way humidification involves being able to control changes in humidity that may be either too high or too low using a single device. Prior work in this area involves small packets, such as the one pictured here, which contain a mix of silica, salt, and water. These packets work to passively control humidity in items such as instrument cases and shipping boxes. Historically, humidity has been controlled using two distinct units, a humidifier and a dehumidifier. Advancements have been made recently which allow the units to be installed and operated through the ductwork of houses. Humidity is typically measured using wet and dry bulb thermometers. The difference between the two temperatures with respect to the dry bulb or room temperature can be used to determine humidity on a psychometric chart. Our approach is unique because it instead aims to actively control humidity using an existing humidifier and dehumidifier. Although we started out with conventional wet and dry bulb measurements, we ultimately decided to code an Arduino. We wired the two units together and connected them with relays to act as one cohesive unit. Before continuing, we wanted to take a moment to address the concept of an Arduino as it is not familiar to everyone. In short, it is an open-circuit microcontroller that can be programmed for various applications. It can collect measurements in real time and send the data collected to a computer. Although it has various sensors, we used one that measured humidity over the course of our experiment. We also coded it to turn each device on or off at specific humidity thresholds. We used two Arduinos in our experimental setup. One was connected to the humidifier, while the other was connected to the dehumidifier. It recorded humidity measurements, overall test duration, and time between humidity changes during testing. Wrapping up the background, we wanted to discuss the implications of our research. It is important because humidity control has various applications in day-to-day life. Existing units are bulky and require frequent filling and emptying. Our method results in more effective use of water and electricity. Ultimately, it could be simplified into one wall unit for use in homes. It can result in increased independence for those who cannot fill and empty the tanks manually. It also has the potential to provide a better environment for technology, cigar, and instrument storage rooms. For this experiment, we referenced existing whole home humidifiers and dehumidifiers. We also looked into humidifiers that can be installed in large-scale greenhouses. Finally, as mentioned before, we researched units that can be installed into the HVAC systems of houses.
The idea of this test is to see what degree we can control the humidity in a controlled environment and how long it would be possible to maintain the humidity. The controlled environment of this experiment is a small greenhouse that is sealed off, and inside the greenhouse there is a dehumidifier and a humidifier that are meant to control the humidity. For the setup, two extension cords would be wired to two solid-state relays in a junction box. Two Arduinos are then wired from their relays to the solid-state relays. The Arduinos are wired to the input terminals, and the extension cords are connected to the output terminals of the relay. The Arduinos were used to control power to the humidifier and the dehumidifier. 4 tests were conducted. The first set of experiments utilized thermocouples, which would measure wet and dry bulb temperatures. The second set of experiments used the Arduinos. Experiment conditions. Two different humidity conditions were tested, between 45 and 55% and 75 and 85% relative humidity. All tests were conducted in the lab, which would greatly impact the results of the experiments. The variables that were being measured are the relative humidity inside the greenhouse and the time taken to reach the desired humidity levels and the duration of time controlling the humidity in the greenhouse. There were many variables that came to play with the experiment. One major variable is the humidity of the lab. Usually the lab is very dry, only having a relative humidity as low as 20%. This caused the humidity in the greenhouse to decline substantially when exposed to the external environment. The settings of each device also played a big role in the experimental results. For example, if the humidifier was set to 45% relative humidity, it would take a longer period of time to reach desired humidity levels than if it were to be set to 90% relative humidity. Another variable that came to play is temperature. Temperature, which was usually constant, could potentially impact the humidity within the chamber. Measurement techniques. For the two preliminary tests, we utilized thermocouples which were connected to a multimeter for measuring the dry and wet bulb temperatures. For the wet bulb temperature, we wrapped a damp cloth around a Type K thermocouple, which was connected to a multimeter to record the wet bulb temperature. For the dry bulb temperature, we used a Type K thermocouple as well, connected to a multimeter to record the air temperature. The two values were then used to find the relative humidity using a psychrometric chart. The second set of experiments measured the relative humidity via a humidity sensor within the actual Arduino. Now for calibration, the Arduino would self-calibrate when first running the program. However, the thermocouples were not calibrated but were measured against other thermocouples to make sure that the temperature values were within reason. Now the process of the actual experiment. Two extension cords were plugged into the wall, and the Arduinos would then be wired to the input terminals of the solid-state relays. Both Arduinos were connected to two computers, which would run the program. The program utilized C++ to execute the program, and if-else statements were used to control the power to each device in the greenhouse. Based on the if-else statements, power would be supplied to each unit. For example, when testing for the 75 and 85% relative humidity range, both Arduinos were set to a threshold value. For example, if humidity is less than 85%, then switch relay 1 to close. This means that the power will be supplied to relay 1 as long as the humidity remained below 85% relative humidity. After the code in the program is satisfactory, then we would set the humidistat settings in both the humidifier and the dehumidifier. Once the setup is complete, we run the program, and the Arduino would send power to each device based on the thresholds established in the code. A live data feed would then be monitored for the duration of the experiment to make sure nothing was going wrong and that the settings of each device was satisfactory.
This slide shows the Gantt chart that was used throughout the semester. Following the chart enabled us to complete the experiment on time.
Our budget wasn't used as much as we expected, due to the support of Hoover providing us with the greenhouse that we use to control our environment. We luckily were provided a humidifier and dehumidifier as well from our group members' families and Hoover as well. We could have expected around a $300 to $400 budget needed for the scale of a project. However, we only spent about $30 in total. Our major risk with this project was the electrical wiring components that we used to connect relays and prevent startup time with. We practice electrical safety, but our PPE could always be improved to prepare for worst-case scenarios. In future experiments, we can include the usage of electrical gloves and wire protection across all of our wiring. Other risks were nullified by proper training among other methods displayed above.
Results section, we have four plots representing our three different test runs. First of these plots shows our first test where our target value was 45 to 55%. The humidity data was recorded manually using alternators, and as you can see, the plot is not very consistent, ranging anywhere from 35 to 75%. The second plot is the repeat of the first test with a couple of changes. The first of which was the addition of a fan to better circulate the air in the greenhouse and hopefully yield some more consistent readings. And the second change was that the devices were manually turned on and off in order to maintain the humidity level with more consistency. As you can see, based on the data, these changes were effective, and we were able to keep the humidity within a target range of about 45 to about 55%. The third plot consists of data measured by the IoT Maker Kit Arduino, which we were able to code to read the humidity in the greenhouse and then use that reading to determine if it needed to turn on the humidifier or dehumidifier to maintain the humidity within the target range. For the test that we ran with this system, we chose a higher target range of 75 to 85%. And as you can see in the data, the system worked really well because we were able to maintain within 70 to 83 plenty of room spare. The final plot is an extension of test 2, where we opened the door to the greenhouse for a short amount of time after we had gotten the data we needed. And as you can see, when we did that, the humidity begins to fall. And when the greenhouse door is closed, the system is able to return the room levels to where they were before and where we wanted them. So all that taken into account, we're pretty happy with the data. Each test was better than the last, and we were able to accomplish our goals of staying within the ranges that we wanted.
During the testing conducted in the enclosure, there were numerous different factors that could have contributed to some inaccurate data. The enclosure was not completely sealed from the outside environment due to a few things. The base of the enclosure was just resting on the ground, which could have allowed some air to seep under. We also did not test the enclosure for any leaks along the seams and such. While testing, we were also required to open the door of the enclosure to turn on the humidifier once the relay sent power to it. It was only about 4 seconds that we had the door open every time the relay kicked on, but still allowed a substantial amount of air exchange between the environments. We also did not have the door zipped all the way down to the ground for the majority of the tests. Another source of error could have been the Arduinos. The test required us to have 2 Arduinos set up, one that would trigger power for the humidifier and one that would trigger power for the dehumidifier. We noticed while testing that the Arduinos read slightly different measurements of relative humidity. The assumption here is that our Arduinos weren't calibrated correctly, with the humidistats giving us incorrect readings and contributing to our devices powering on and powering off at the wrong times. The wiring suggested no issues and the code ran smoothly throughout our testing.
In conclusion of our tests, we determined that we were able to control humidity within a range of 10%. Any note of error was brought about by human interaction with the greenhouse or coating errors. There were also conditions of the greenhouse where not closing it all the way could have impacted all three tests. Of course, there was uncertainty with all the makeshift relays and greenhouse setup, but we can still assume temperature was constant unless tampered with purposefully. This two-way humidification experiment can be used for a better understanding of humidity control in our different testing climates. Whether in factory or home maintenance, humidity control was shown to be done correctly here and hopefully in the future. Strides can be made to bring this experiment to life in those areas and hopefully in the workplace.
We would like to thank Professor Hoover for his guidance and support throughout the semester. He pushed us to learn wiring methods that we otherwise would not have gained exposure to. We would also like to thank our TA, Shavat, for his continued time and effort in helping us to achieve our goals. Finally, a huge thank you goes out to Andrew's parents for letting us run the experiment with their dehumidifier.